Assalamu alaikum and welcome to lecture number 27. You understand these lectures are taken from the book Digital Signal Processing, a Practical Approach by Emmanuel I. Fisher, and we are discussing about the finite impulse response filter FIR and infinite impulse response filter FIR. So in the previous lecture we talked about the FIR filter and we discussed about some of the methods that are used for calculating the coefficients of the FIR filter. You understand by FIR we mean that the response will have some finite values. In this lecture we are going to talk about the IIR filter or infinite impulse response filter design method. First we'll talk about the steps of the filter design for the IIR case, and then we will talk about the one method that is pole zero placement method, and we'll just briefly introduce the second method, that is impulse invariant method. So in general you understand that FIR filters can have exactly linear phase response, but in case of IIR you understand that the main qualities of the IIR system are short cutoff filters and high throughput, as IIR filters, especially those using elliptic characteristic, will give fewer coefficients. Regarding this point we have also done some of the examples, and where we find that in case of IIR filters the number of multiplications required, they are few. Similarly the number of additions required in case of IIR filter, although the response is same, right? For the same frequency response, when we compare the two filters we find that IIR filters required not only the number of less multiplications, but also the number of additions are reduced and number of storage locations are also reduced. So that means the IIR filter will have high throughput in comparison with FIR filters. Also, analog filters can be readily transformed into equivalent IIR digital filters meeting the similar specification, and you know that this is not possible with the FIR filters as they have no analog counterpart. The design stages for digital IIR filters are similar as the FIR system, that we specify the filter specification, then we approximate or find the coefficients, or coefficient calculation is the second step. Similarly, realization, which is simply converting the transfer function into suitable filter structure, and the fourth is the analysis of errors that would arise from representing the filter coefficients and carrying out the arithmetic operations involved in filtering. And also the fifth one is the implementation, where we build a hardware or write software codes. So let's start with the pole zero placement method. That will be the first method we are going to discuss after the IIR filter design step discussion. The input-output relationship for the IIR case is as shown here. So from the equation you can tell that this is basically an infinite impulse response system, because k runs from 0 up to infinity. This can also be written in terms of the difference equation as summation k running from n up to k running from 0 up to n, ak x of n minus k, and similarly for the bk. So I think you can tell the difference, because previously we were using the book of the Oppenheim. There we used ak for the coefficient of y, whereas bk was the coefficient of x. So I hope this difference will not confuse you. Anyway, in this book we'll denote the coefficient of x of n by ak and coefficient of the output by bk. The system function for this equation can be written as this one. So all these things should be now clear to you because we have done these equations so many times. So it can be written a0 plus a1 and so on divided by this one. So in summation we can write k running from 0 up to n ak z of minus k over 1 plus summation k running from 1 up to m bk z power minus k. In the factored form, you also know that we have expressed the system function in the factored form also. So in the factored form, we can write it h of z equals to k z minus z1, z minus z2, and so on. So you understand these z's, they represent basically zeros. You understand what is a zero. Zero is the value of z, right, for which h of z becomes 0. Similarly, for these are the poles, they are p1, p2, and so on, and this is expressed in the factored form, very clear from the expression. You also know the poles are the values of z for which h of z becomes infinity. For the stability, you understand that poles must lie inside the unit circle. You understand that the ROCs are the values where the system is the system response converges. So for a system to be stable, the ROC in general, ROC is the region that is outside the outermost pole. But for the case of the stable system, the poles must lie inside the unit circle, whereas you understand from the previous discussion that there is no restriction on the locations of the zeros. Also, as per previous discussion, you understand that for the same system function, IIR filter normally requires two fewer coefficients in comparison with the FIR system. FIR system has the plus point of having the linear phase. The IIR filter are used for the sharp cutoff and high throughput. They can become unstable or their performance significantly degraded if adequate care is not taken in the design of the IIR systems. So this is quite similar to what we have done for the FIR system. So similar to FIR system, the IIR system or the IIR filter design has the following stages. So you understand the first stage is specification of the filter, and the important specification at this stage are the function of the filter, whether we are using it for a high pass, low pass, band pass, and so on, and the desired frequency response or the desired performance, what ripples we want in the stop band, what ripple we want in the pass band, what should be the transition band, and so on. So these are the filter specification. Then the next step was, if you recall, the coefficient calculation or approximation of the filter, where we select one of the number of methods available for calculating the coefficient values. In this case, we need AK as well as the BK, and we select them in such a way that the specification given stage in the first step are satisfied. Similar to the FIR filter design, the third step is realization. Realization means we convert the transfer function into some suitable filter structure. You have been taught about the different structures and so on, so I think that's quite straightforward. The typical structure for IIR are parallel and cascade, and you understand that these are based on the expression for the system function. We can express the system function in terms of the factored form. So when we express it in the factored form, we can have the cascade form realization. The fourth step is the analysis of errors that you understand would arise from representing the filter coefficients, because normally we have the filter coefficient can have infinite values, but in digital implementation we can have only we can represent them using the few bits, that may be 16-bit, 8-bit, 12-bit, and so on. And the final step is the implementation, which involves the building hardware or writing the software codes and carrying out the actual filter operation. So again, this is the flowchart representation of the design stages for the filter. So you understand the first stage is the performance specification or the filter requirements. Then we calculate the coefficients of the filter, and then we realize them using some suitable structures, and then we analyze with the finite word length effect. Does it meet the required qualification requirement or the specification? If it doesn't, then we can go for the realization structure. We can realize it in different ways. We can also go for the calculations, and we can also modify the performance specification requirement. So also we have to discuss this type of figure in the previous lectures while we were doing the FIR system. So for frequency selective filters, whether they are high pass, low pass, or band pass, the frequency response specifications are often in the form of tolerance scheme as shown here. So here we have a new parameter, that is, we call it pass band ripple parameter. This is different from the what we have done for the IIR system. The pass band ripple is basically the difference between the minimum and the maximum deviation in the pass band, right? So that's your if you look at this figure, so in case of ideal filter, you understand these dashed lines, okay, so they represent the ideal filter. So in case of ideal, you also can see that this is basically a band pass filter, okay. So all the frequencies that are less than fs1, they are 0, they should have 0 magnitude, whereas in those frequencies that are between fs1 and fs2, I'm talking about ideal, right? So they should have one value of 1, and those frequencies that are greater than fs2, they should be 0. So if you compare ideal with the practical, you can see that in ideal case we have flat pass band, right, and sharp, this one, right, break response, what we may call it, or what normally it is called. But in case of practical filters, we have ripples here, we have ripples in the stop band, both the stop band, because this is a band pass filter, so we have stop band here, and we also have a stop band here. Also the third thing, that is the transition band. So we have, in practical case, we also have a transition band, right, which is the difference between fp2 and fs2. So this represents basically a transition band. Similarly again, so in case of practical band pass filter, we have basically how many bands? The stop band, transition band, pass band, again transition band, and stop band. Whereas in case of ideal, we only have stop band and also here stop band, so there's no transition band in the ideal filter. So I think you are familiar with these notations, that sigma of p represents the pass band deviation, right, and this new parameter impulse square that represents the passband ripple parameter, and that's the difference between the minimum and maximum deviation in the passband. We have stop band deviation represented by sigma of s. This is same what we had in case of FIR system. Again, we have two H frequencies, FP1 and FP2, right? So these are the passband H frequencies, and why we have two? Because this is a bandpass filter, so one is the lower H frequency and one is the upper H frequency. And similarly, we have stop band H frequencies, that is FS1 and FS2. So I think that's quite straightforward, and you might have understanding of it. You also know that this is versus frequency. Okay. Coefficient calculation methods for IIR filters. Simplest way to obtain IIR filter coefficient is to place poles and zeros judiciously in the Z plane such that the resulting filter has the desired frequency response. This approach is known as the pole zero placement method, and it is useful for very simple filters where filter parameters such as the passband ripple need not be specified precisely. A more efficient approach is to first design an analog filter satisfying the desired specification and then convert it into an equivalent digital filter. Most IIR filters are designed using this way. So let's first consider the pole zero placement method. So you understand that a pole is a zero is a place where the response is zero, and a pole is a place where the response is peak. So placing a zero at a given point in the on the Z plane, the frequency response will be zero at the corresponding point. Similarly, placing a pole will result into a peak at the corresponding point. Thus, by strategically placing poles and zeros, we can obtain the frequency selective filters. The important point is that poles and zeros must be either real. If they are not real, in that case they must occur in the complex conjugate pair. So you understand, by real means that they will exist on the real axis, right? That is the along x-axis. So both should be either along x-axis. If they are not along x-axis, then they should be in the complex conjugate pairs. So let's have an example to see how the pole zero placement method works. Let's take an example. For example, we have to design a band pass digital filter having the following specifications. So the first thing is that rejection, right? So complete signal rejection at DC, that means at 0 Hz, and at 250 Hz. A narrow pass band centered at 125 Hz, 3 dB bandwidth of 10 Hz. So assuming the sampling frequency of 500 Hz, obtain the transfer function of the filter by suitably placing pole zero, pole zeros in the Z plane, and we also have to find the difference equation. So that means the filter will have characteristics something like this. Let me plot the tolerance scheme. So a 3 dB bandwidth, right? So 3 dB is a point where the response is 0.07, right? So because in the pass band ideally it has 1, right? But there are some ripples that you understand, And then so it's a bandpass filter first thing, so that means the frequency will be the response will be 0 for some values of frequency, and then it will gradually move up, right? And then we have something like this, and then we have the frequency that is going down, the response is going down. So the center frequency is 125 hertz. Now the 3 dB is the point where the response is how much? Response, for example, this has value of 1, so at 3 dB it will have value of 0.707. so we'll have 3 dB 2 points of 3 dB, that is this one, and again here it will the point where its response is 70, right? So something like this. So that means the bandwidth is what they say, for example, so this is the bandwidth, right? Now this is right, so that's 10 hertz. Okay, maybe it's visible to you because I have selected not a good option. Anyway, so this is the 10 hertz bandwidth, which is right 3 dB bandwidth, so that's what it is. And this is, for example, your linear frequency axis. Okay, now the first thing is let's place the poles and zeros on the Z plane. So because we are told that we want a complete rejection at 0 and 250 hertz, so that means, so to find the pole zeros, right, because we want complete rejection at 0 and 250 hertz, so that means at those two frequencies we'll have zeros. So the angles are 360 degree, right, multiplied by 0 divided by 500, because 500 is the sampling frequency. So that means we have a 0 at 0 degree, again a second 0 we'll have at 360 multiplied by 250 divided by 500, so at 180 degrees. So something like this. So this is the unit circle. It's not exact, but anyway, so this is 0 degree, we have a 0 here, and we have another 0 here at 180 degree. For the pass band to have centered frequency, right, so we find the poles, because at that point it will have the high values. Okay, so we have plus minus 360 degree multiplied by 125 divided by 500, it gives 90 degree, right, because it's not on the real axis, right? That's your real axis. So if it's not on the real axis, so that means we'll have a conjugate complex conjugate pair of poles. So that means one will be here. You understand, we denote the pole by cross. Okay, so we have a pole here and we have a pole here. Okay, now we have a pole but not on the unit circle, right? I have this I have plotted it here, but it's actually not on the unit circle. We first have to determine the value of the R. So we just know the location, that is at plus minus 90 degree we have two poles. And why we take, you understand why we take the complex, right? Straight away we could have found like this, because no need for this. We just multiply 360 multiplied by 125 by 500, which gives the 90 degree, because it's not on the real axis. So because it is must that they must be either real or they must be conjugate, right, complex conjugate. So if you have a pole not on the real axis, that means we'll have two poles, right? So one, this is because on 90 degree, so we'll have one at 90 degree and one at minus 90 degree. Now to find the R, so there we have an approximate relationship between bandwidth and R, which is given by this equation. Okay, so that means 1 minus bandwidth divided by the sampling frequency times pi, right? So you understand bandwidth is 10 and the sampling frequency is 500, so you divided this by this, so from this you get something like 0.0 0 to value of pi is something like 3.14, right? Or you have the calculator, you can straight away calculate it. Once you calculate this, you subtract it from 1, so you will get the approximate value for r, which is, so that comes to be r equals to 0.937. So something like this one and this one, right? So based on these values, we can find the transfer function. So transfer function is given as, because we have two poles on the unit circle, so we have z equals to z minus 1 times z plus 1. So this is for z equals to 1, and this is for z equals to minus 1. So you understand this is the point where it's 1, and this is the point where it is minus 1. So you put this one, then again divided by, because we have two poles, two zeros, and we also have two poles, so we can write z equals to r e power j, right? And the angle is which we have found for the pole is 90, and 90 is pi by 2. So we have z minus r e power j pi by 2, and z minus r e power minus j by 2. You understand, because they are complex conjugates. So if this is pi by 2, j pi by 2, so this will be minus j pi by 2. Okay, so on simplification we get something like this. So this is the system function for the required filter. So because we know the system function, so once knowing the system function, we can make its realize it, or make its structure. So it will be something like this. So I think that's quite straightforward. Again, by looking at this one, we can just find the difference equation. That's quite simple also, because h of z, you understand, h of z equals to h of z equals to something like, so h of z equals to y of z or x of z. So that means x of z is divided here, so just multiplying h of z with x of z will be equal to y of z, and that's straightforward, because you understand in time domain the output is equal to the convolution of the response with the input, whereas in frequency domain output equals to the product of the input with the system function. Okay, so that's straightforward. H of z multiplied by x of z, so you can say that x of z is here, right? And so because this divided this side, we can bring it to other side, so we multiply this with y of z, right? So that means that's straightforward. Okay, so it will be something like y minus this one, right? That will be y of z times y of z, this thing. So when we take the inverse, so inverse of y of z will be y of n, and inverse of this will be 0.8796 into y of n minus 2, because z power minus 2 multiplication means delay by 2 units. Okay, so again similarly for x of n, so it will be x of n minus x of n minus 2. So I guess that's quite straightforward, right? So again, this is the pole 0 plot for this problem. So if you have any confusion, we can discuss this in the class. So let's take one more example. In this example, we have to design a filter, that is notch filter or band stop filter, and the specification of the filters are that the notch frequency is 50 Hz, so that means we have to stop the frequency around 50 Hz, right? And again, the 3D bandwidth of the notch filter is plus minus 5 Hz. So I hope you're familiar with the 3 dB. 3 dB points are the points where the amplitude is 1 over square root of 2, or it's roughly 0.707. So you based on the figure shown here, you can see that the this is the notch filter. And why this is notch filter? Because you see it stops just this part of the frequencies. For all other frequencies it has response equals to non-zero, right? Or roughly we can say that this is basically equal to 1. So the response is 1 for all the frequencies except those frequencies that are around 50 hertz. The 50 is the center frequency, so the bandwidth of this is, as given here, is plus minus 5 hertz. So you understand that response is 1 and then it slightly starts decreasing. So the point where the response is 0.707, that will be called the 3 dB point. So one point we have here and we have another point here, 3 dB, right? So the difference between the two frequencies is of this one, right? So we have somehow this response, okay, I mean as plotted here. Now the problem is that we have to find the filter coefficients using the pole zero placement method. So you understand that's quite straightforward method, because we are given that we have the notch frequency that's 50 hertz and the sampling frequency is 500 hertz, right? So you understand the notch concept. So to first we let's find the zeros for this one. So to find the zeros, because zeros are the values of the z, where h of z will be 0. So to find the zeros based on the given information, so 360 multiplied by 50 divided by 500, this will give us plus minus 36 degrees, because it will just give you 36 degrees, because but you know that poles and zeros either must be real, or if they are not real then they must be complex conjugates. So that means because this one gives us 36 degrees, so 36 degree means that it is not real. When it is not real, it has to be a complex conjugate pair. Okay, so that means we should have two zeros that are at plus 36 degree and minus 36 degrees. So as shown in the figure here, this is your first zero, right? This point is the zero where we have angle of 36 degree, and this one is, again, you understand that for the finding angle you go counterclockwise. So this is the plus angle, so if you go the clockwise, that will give us the negative angle. So we have this one minus 36 degree. Okay, so again finding the r. Okay, so r equals to, this is from the previous example, r equals to 1 minus bandwidth divided by fs times the pi. So bandwidth in this case is, so the bandwidth is 10, because it's plus minus 5 dB, right? So that's your one frequency and that's the other one. Okay, so the difference between the two is given as plus minus 5, means 10, right? Because this point will be 50 minus 5, that's 45, and this will be 55. Okay, so the difference will be 10, so that means you just put here 10. Okay, 10 divided by sampling frequency is given to be 500, so this is somehow 0.02, and then you multiply it by pi, so right, and then you subtract it from 1, so it will give you radius equals to 0.937. Okay, and for the case of the poles, we have the values, angle values, which are same as this one, right? So that's exactly, so that's your first pole and that's the second pole. This is your 1 0 and that's the second 0, and you know r. So once you know r, you also know the angle, so we can straight away put the value of the angle and we can find the h of z. So by putting value, so z equal, so we can express h of z as z minus exponential to the power minus j36 and z minus exponential to the power plus j36. Similarly for the case of the poles, because we have r, e, j, theta, so again we have z minus r is 0.937 exponential e power minus j 36, and again z minus 0.937 exponential e power plus 36 degrees, right? So on simplification we get something like this. So that is the system function for the required filter. So this can also be represented in the difference in terms of difference equation. So simply you just say this is equal to basically x of y of z divided by x of z. Okay, so when you know right, so I hope that's straightforward to find the difference equation, and that's also very easy to make the structure of the resulting filter. So let's talk about one more technique for the IIR filter design, that is how to approximate or calculate the coefficient of the IIR filter. So the second method we are going to discuss is the impulse invariance method. The pole zero method is not that efficient. The more efficient approaches for IIR filter design are those that are based on designing the analog filter first, right? So and then converting it into an equivalent digital filter, right? So the approaches are some of them are the impulse invariance method, match Z transform method, and bilinear Z transform method. So the first method we are going to discuss is the impulse invariant method. That's quite straightforward, like we have said here, that first we need to design a filter in analog domain, and then the resulting system function is converted into equivalent digital filter. So starting with a suitable analog transfer function, so the first step is that we find the suitable analog transfer function, which we represent by h of s. Here s indicates that we are in the Laplace domain. Okay, then we obtain the impulse response h of t by taking the inverse Laplace transform of h of s. So once we do this, we get the impulse response of the filter we need. After that, we sample h of t to produce h of n of t, right, which is the discrete. Okay, so once we obtain this h of n of t, we obtain the desired system function by taking the z transform of h of n t. So for example, this is the system response, impulse response, right? And you understand impulse response is basically in time domain. So for example, this is the impulse response of the required filter we want to design. Then we just sample it. Okay, so when we sample it, we get the sampled version of this one. So I hope most of you are well familiar with this one, because we have done these type of things while doing sampling the continuous time signals, right? So you understand what issues arise here. So the important issue is that we must have the sampling frequency which is at least twice or higher or more than twice the highest frequency component present in the signal to be, or the system response to be sampled, right? So in case we do not meet this one, which is called the Nyquist criteria, so if we do not meet the Nyquist criteria, you understand, we'll have aliasing, you understand, because sampling a signal or the response of a signal in time domain basically corresponds to the producing replicas of the signal in the frequency domain, and those replicas are around the sampling frequency. So if we meet these Nyquist criteria, then there will be no overlap between the different replicas of the original signal. But if we do not meet the sampling criteria, then the replicas will overlap and we have the distortion that is called the aliasing distortion. So I think with this we end the lecture for today, and see you in the live session. Okay, in the next lecture, from the next lecture we will continue from this slide. So Allah Hafiz.